Alright, in this segment we're going to be tying together the concepts of gravity, conservation of energy, potential energy, kinetic energy, and total energy in a system. To do this, we're going to be looking at some definitions. We'll be giving an explanation, and then we're kind of going to look at an application. Alright, to start off with, let's run over some quick definitions. First of all, potential energy. This is the energy of position. This is where an object gains energy, stored energy, based on its location. And in this particular instance, its location as relative to a gravitational mass. Okay, kinetic energy. Kinetic energy is the energy of movement. This is the more movement that the more motion, the more velocity that an object has, the more kinetic energy that it has. Conservation of energy says that energy is neither created nor destroyed, but simply transferred from one form into another. So this would mean that the total energy in a system is going to be equal to the sum of all of the sources of energy. For example, potential energy plus kinetic energy, if that's all we have in a system, will be equal to the total energy. One last quick reminder, an ellipse is a form that has an oval-like shape with two foci. All planets orbit in ellipses where the primary mass that it's orbiting is in one of the ellipses. So, for example, our Earth has an elliptical orbit around the Sun. Let's look at a scenario so that we can take a look at how all of these things work together. First question I have for you. If we have a satellite that is orbiting the Earth in a circular orbit, which is basically an ellipse where both foci are right on top of each other, does this satellite have potential and kinetic energy? Well, let's take a look again at our definitions and see if we can figure that out. Does our object have a distance between itself and the center of mass of another object? Well, clearly it does. So, at position A, our satellite has potential energy. Now, does it have kinetic energy? Well, it is moving, therefore it has kinetic energy. We know from our conservation of energy concept that the potential energy plus the kinetic energy will equal the total energy in our system. So, if we have the total energy in our system is the addition of our potential and kinetic energy, take a look down here at position A on our graphs. You can see that our object has kinetic energy, it has potential energy, and if we add the kinetic and potential energy together, we get the total mechanical energy. Now, in a perfectly circular orbit, the speed, the velocity, does not change. It maintains a constant velocity, giving it uniform circular motion. With that being the case, kinetic energy is going to be the same. The distance between our satellite and the center of mass will remain the same. So the potential energy stays the same, and we know that our total energy will stay the same. So in this particular scenario, where we have a circular orbit, potential energy and kinetic energy remain constant. But this is not true of all situations. Let's take a look at this scenario. Let's see how this potential energy, kinetic energy type of thing switches off and changes. First of all, where do you think we have the greatest potential energy? At position A, B, C, D, E. Well, remember, potential energy is the mass times the gravity times the height. So the further the distance is, the greater the potential energy. So we have the greatest potential energy at position C. Where do we have the least potential energy? A, B, C, D, or E? Well, the area closest, we would have the greatest potential energy. Now we know from the law of conservation of energy that the total mechanical energy is going to remain constant throughout. So, when we have the greatest potential energy, this is also going to be the time when we have the lowest kinetic energy. It's just the same as if we were to take a ball and throw it out away from ourselves. When it reaches the top, it has the greatest amount of potential energy and the least amount of kinetic energy. And then as it starts going back, it speeds up again until it has the least amount of potential energy and the greatest amount of kinetic energy. But you can see at position B, we have our kinetic energy is a little bit less than our potential energy. At position D, our potential energy is noticeably greater than our kinetic energy. And then these types of energy keep switching off back and forth. Now this ties directly into Kepler's laws of planetary motion, because he says that a satellite, when it's the furthest away from the object that it's orbiting, will move the very slowest, and it'll move the fastest the closer in that it goes to its planet. This matches with our idea of the conservation of energy. All right, key things that I want you to remember. Energy is conserved. And it's not just conserved when we're talking about roller coasters. It's conserved when we're talking about satellites and satellite motion as well. Kepler's 3 laws help us to understand how planets move. Newton's laws explain to us why they move in that particular way, including Newton's universal law of gravitation. So you can see in this one example, we are tying together many of the concepts that we've already been studying, from the concepts of velocity and acceleration, circular motion, centripetal forces, potential energy, kinetic energy, and total conservation of energy. I hope this helps. Have a good day.